7, logistic growth. All right, so population projections first became important of political philosophers, blah, blah, blah. And so in other words, what they're looking at is they recorded the population every 10 years. So here's the year, here's the population. First thing you'd probably want to do is graph it, see what it looks like. So here I have years all the way to the year 2000. If I only graph part of it, so I only graph from 1790 to 1860. And this is something I don't mention often, but you ought to get good at doing. If you look at this graph here, you might say, well, those aren't those same numbers. You never want to graph huge numbers like this. And notice this is populations in millions. And you want these, you want your values to be kind of the same. In other words, you don't want this to go from 0 to 100 and then that 0 to 10. Otherwise, you have a skewed. Well, if I continued this and I go a few more years to 1940, hopefully you can see this looks very exponential. Something's kind of happening a little bit. So I could model this, and I mentioned this before. Many of you guys have to take biostats. I don't know if they do regression in there, but you model your data with an equation, and in this case, this is the equation. It's an exponential equation. It fits it. But now if I add those years, I notice what's happening. This model no longer looks good with this data because it's saying the population's shooting straight up, and it's really not, because your rate of growth is starting to decrease at a particular year here. And again, we could assume, my guess would be birth control was invented. I mean, that would be my guess. Why did things start to slow down? Men go off. I guess they say there are more babies, though, before they go to war. I don't know. All right, so this would be modeled with this equation. How in the world would you know that? Because I told you. All right, but this is an actual special equation. This is called a logistic model, a logistic equation, where you can see there is a piece of exponential in here, but it's on the bottom, meaning that as the bottom's getting larger and larger and larger, this is getting smaller and smaller and smaller, because a fraction, if you have 1/2, 1/4, 1/6, 1/8, it's getting smaller and smaller, right, as the bottom's getting larger. And so what we have here is called a logistic function that is written in this form, where L is called the carrying capacity. This is what I mentioned last class, that I said I always think of a fish aquarium. You buy yourself an aquarium, you put a bunch of fish in it, and eventually only so many fish can fit in that aquarium. That's what carrying capacity is. Your population can only grow so much, and then people start dying out, okay, fish or whatever. So this is the largest population a particular environment can support. What's so nice, you will like about this, because if I didn't tell you this, I would say find the inflection point. Find the first derivative, the second derivative of this ugly thing. So nicely it works out, the inflection point actually occurs at this carrying capacity divided by 2. That also tells you where your population is growing the fastest, because you're going to have the steepest slope there. So this L over 2 tells you, and this is also called the point of diminishing returns, but it gives you your inflection. So what I could do is I could look at this again, where I have constants here, my L, how much my population can stand. This is just some constant in front here, my K constant up top. This is that e to the minus kt we've already looked at. I could just look at different values for my carrying capacity, okay, and say, well, what if it's 1, what if it's 2, and look at the graph of each one of these and see that, well, starting out, it looks like this piece right here, if I stopped right there, right away, that's an exponential function. Continue on with this, I notice that the concavity is going to actually, and the concavity changes where? At the inflection point. Okay, so what we already talked about, that's what inflection point tells you, is where the concavity changes. And then it starts going concave down. Okay, so concave up to concave down, and then our inflection point. And then our carrying capacity. And a lot of times you'll draw a straight line to see, this is kind of like what you're used to looking at with the logarithms, that you're getting really, really, really close to a value, but you're never really touching that value. You're getting, of course, now, and that was for values of L. If I say, well, let's just look at one particular L, my carrying capacity, and I look at different values of K, well, I can see what's happening if this constant here is very, very large, I can see the logistic function is approximately exponential for small values of this t. This is my growth rate, my k, so it would make sense if this k is large, it's growing very quickly. If k is your growth rate. If k is small, then it's not growing quite as fast. So this value right here is telling me what my growth rate is.
Is the carrying capacity considered a horizontal asymptote or no?
Yes, it would be, yeah. All right, so example 1, if T is in years since 1990, one model for the population of the world, P in billions, is this. You can look at this right away and say, yeah, that looks just like the logistic function that she just gave. And that's one thing like I probably would put on your formula sheet. I would give you the logistic function. That way you can go and look on your test and say, well, that looks like that. So I know, these type questions. What does the model predict for the maximum sustainable population of the world? 40. So in other words, what we're doing is we're looking at the carrying capacity. So some of these are easy, you just look at it. But you have to understand this formula that that's our L, this is our carrying capacity, and so I just simply look at that value.
So that's why I keep getting wrong.
According to the model, when will the Earth's population reach 39.9 billion? What do you do? Yeah, put that in for P, and then I have an ugly thing. I wanted to say it. So now I solve this for T, because it says when, what time. So away I go. What I did is I just simply flipped these around. I brought the 39.9 over here. I took this piece and brought it to the top. So all I did was just kind of flip those. Kind of carry this along the way. I know most of you would probably go ahead and just get what that equals, but I'm just carrying it along the way. I'm going to subtract 1 on both sides. And then I'm going to divide by 11. Okay, again, there's no problem with you guys doing this each step. I'm just showing you in kind of one big step. I divided both sides by 39.9. I subtracted 1 on both sides, and now I'm dividing by 11. So now you can see I'm to the point where how we solve this is take natural logs of both sides.
If you give a question like this and you're asked to solve for it, do we have to do all this work, or can we just use the calculator to just say?
Just the calculator. Yeah, would be fine.
Or say
It's one of those that I always say, the more steps I know students don't like to show steps, but the more steps you show is better. Because if you get it wrong, I can say, oh, they just made them, Cindy forgot to do 1 over B here and minus 1. But if you just put an answer, then it's right or wrong. It's kind of like multiple choice. Well, I'm just trying to help the class see in steps, step by steps. Here, sorry this got smaller, I guess you can still see it. I finally got a number here. Okay, so I got this number and log of both sides. I mean, hopefully this is something most of you remember from algebra. And so that cancels, this comes down. This again goes in my calculator. Okay, and so then I divide both sides by negative 0.08 and I get this value. Okay, this is definitely, you will 100% have a problem like this on the test. And it'll look just like this, that you'll go through the steps of solving. You'll be giving the logistic function and you'll go through the steps of solving for T, for time. And so in this case, my 105, I started 0 at 1990. So the time that it reached the 39.9 million, I think it was, would be in 2095. So I just add that back. This is kind of, I see students miss this. You're just so happy when you finally get this answer, you write it down, right? I got an answer, woohoo, and you move on. But you got to remember to plug this back into your definition. All right, example 2. The Toja Hola Hoba Hola Solas, yeah, those people. Mayan Indian community in southern Mexico has available fixed amount of land. The proportion P of land, so this gives me a proportion, a percentage, in use for farming T years, so again time. You can see all these are good functions for things that happen over time, populations. But in this case, we're going to use it for a proportion after 1935 is modeled with this. What proportion of the land was in use for farming in 1935? What?
1/4
1/4? Where'd you get that from?
Because it said they wanted the proportion, so it started from 1935, so you put t at 0. Since it's like, yeah, 1/4.
Yeah. All right, so 1935, number of years after 1935 would be 0. So your time is 0. You plug that in and you get 1/4 or 25%. Okay, so it's just, a lot of this is wording. How would I know to do that? You know, what proportion, this right, and that's again why I would do things like this. This gives me the proportion. What proportion? Oh, I guess I'm just going to use that function. I'm not doing any derivatives, okay? I'm just going to plug in. Why am I plugging in 0? Because it said in 1935, and this model was t years after 1935. What is the long-run prediction for this model? Yes, you do. Just look at it.
What is the long range? Oh, 1.
Because we meant that eventually you'd use all the land, 100%. You don't like, you don't like this problem already, I can tell. So remember, let's forget all these words. If I said, what's the carrying capacity? 1. Okay? So this problem here is the proportion of land being used. Wouldn't eventually you could use all the land? So 1 as a decimal is the same thing as 100%. So in other words, that's like 1.00, which is the same as 100%. So this is saying in a perfect world, they could use 100% of the land.
But they can't reach that according to the graph.
It's kind of like a limit. They could use 99.9999, yeah, type deal.
For this example,
Yes, I like that you did that.
said we can't use physics in this.
When was half the land in use for farming? What do you do?
1.5 would be
P, my proportion, so 0.5. And guess what? You go through those steps we did before, because you know how to do that now, right? Yeah. You'd switch that. You go through all those steps, and you would get your T, your time. So this would be in my notes. I should rework this. Huh. Meaning you should go through these steps. You're going to get to work this. I think this is isn't this a homework problem? Is it?
I think it was.
I think this is the Indian one, yeah. I know this came from the book, but I think it's a homework problem. And of course you could graph it. You look at the half. I mean, I can simply graph this. This is my function. And I look to see when I'm going to hit a half, and this would make sense. Again, you know, I don't see many of you guys graphing. I graph everything to see, does that make sense? And that's when I would hit a half. When is the proportion of land used for farming increasing most rapidly?
Derivative, I think.
The very beginning of this, I said, good God, we wouldn't want to have to find an inflection point. We find it very easily by...
beginning in 20 years.
So L, which was our carrying capacity, 1 divided by 2. So take your carrying capacity divided by 2. Again, that just happened to be the value we just found. That happened to be the inflection point. So that's where it's growing most rapidly. Again, in my notes, I would put this is the inflection point. And Cindy said we found that by carrying capacity divided by 2, which that's my L, which is that value right there. I mean, that way it kind of helps you when you're studying. Otherwise, you just sit and you stare at these notes and go, man, Cindy's notes really look nice. Don't know what they mean, but... Right, Celeste?
Yeah.
I wasn't talking about your Celeste. I was talking about the good Celeste. Oh. All right, 4.8, the surge function, a.k.a. when Vivian steps. All right, this is what the surge function looks like. Guess what? Doesn't that look familiar, that whole crazy thing that we just did? Yeah. And so this hopefully, again, would make sense. You take a certain drug, your concentration goes in your system. I tell ya, a bunch of blues. All right, so again, this goes, well, you should have been able to see that. So this goes up high to a point, and then hopefully the drug starts coming out of your system. As I mentioned before, you could have something that has lots of humps, right, if you continue to take a medication. You know, it's something like diabetics take every day to put into their system. This increases rapidly, as you can see. I know you can't see. This increases rapidly, I keep saying rapidly, rapidly, and then it decreases towards 0 with a maximum, guess what, that problem that you worked, 1 over B. So we actually proved that in the last section, which is kind of nice to see now, you know where the 1 over B. All right, the graph below shows the drug concentration. You can see that graph. For one dose of a drug with a minimum effective concentration shown by this dotted line. In other words, once you get below this line, you're below the minimum effective concentration. All right, when should the second dose be given if the doses are to be as far apart as possible while still maintaining effectiveness?
D or E?
D or E? B. Somebody go with A and somebody go with C.
B.
I think it's D because if I look at, I'm taking the drug, it's going past this minimum because it's still in my system, it's coming down. When it starts to hit there, that's when it's going to be below the minimum concentration. So that's when I need to take the second dosage. All right, the drug concentration for a drug after T hours is given by this. This looks just like that thing we did, the AX e to the minus whatever, BX that we had up here. This is the same type function. All right, so this one is, okay, so this is, I start saying my math lab, a Wiley. They also give you the minimum effective concentration is this value. Is the drug effective at T equals 2 hours? What do you do? Flip a coin and say yes or no. Yeah, just simply plug it in. Is it above 10? Yeah, so that's all we have to do because this has given me the concentration. My T, my time is in hours, so I just plug in 2 here and I see is this above my minimum, which was 10. So again, I think the hardest part of this is every time you see problems like this, you think you have to find derivatives because you're in a calculus class, right? But really read these to see what they're asking you to act. If time T is in hours and concentration C is in this nanograms per milliliters, the drug concentration curve is given by this. This is a different one, example 3. How many hours does it take for the drug to reach its peak concentration?
1.
Peak.
0.
Yes.
0.
That's, no, not you.
1 over B. 1 over 12.
Look at 5.
So in this case, if what's nice about this is the surge function changes from increasing to decreasing. Remember that this was given, and we said, oh, we found that in that, what was it, a fish population problem? That was the max, okay, as Amrit said, that's what you're finding, the max. You could go back and do all that derivative stuff, but we already did this. This is our definition. This is how you find the max. So we just simply plug in our value that we're looking for, 1 over 0.2, and then this gives me how many hours? Where'd I get 0.2? It's that KT. Yeah.
So you don't count negatives also? The formula. Oh, it's the formula.
No, it's negative KT, and so it's just the K value. What is the concentration rate at that time?
Okay, wait, 0.5.
At 5 hours. Don't I have a function that tells me the concentration? Couldn't I just plug in 5 hours? So once again, it's asking me what's the concentration, which is what my function is, at 5 hours. So I just simply plug in 5, and that gives me my concentration. Rated. If the minimum effective concentration is 10, which was given at the beginning, during what time period, is the drug? Well, again, what I can do is I can look at the graph and go a dotted line straight across. You can see that, right? Yep.
Yeah.
And so if I'm looking at the graph, I'm just looking at 10. So this again is a Wiley thing. Well, how do I know that's 1? How do I know that's 14.5? Well, you kind of just look in here and see if that's at 15 and I'm looking straight up. I don't know these, how many, decimals you can be off or whatever. But of course, for me, if you put 1 and 15 would be fine on a test.
Or you can just use the calculator and do that.
Yeah, I'm plugging.
90 or something.
Complications can arise whenever the level of drug is above this 4 nanograms per milliliters. How long must a patient wait before being safe from? Again, we can look at the graph and we can see, well, if it stays above here, basically it's saying don't take this drug again if you still have too much in your system. Wait till it gets below this 4 value. And again, we're looking here is about 20.5 hours.
Is that why you're not supposed to take certain amounts of Advil and all that after like between 8 hours?
Like they'll tell you every so many hours.
How do they, because like each body works different, they just take an average?
I'm
Or do
sure.
Or do they just say, okay, this is what it is, we're gonna put like 10 hours just